Next, I'm going to show you some simple plots. First, a histogram. The hist function, H-I-S-T, can generate a reasonably formatted histogram with just one argument, a vector of numbers. So we know already that salary is a numeric vector. We've been using it for various other examples. I can call the hist function with this vector as its argument, and I'll get this histogram, an example of what the hist function does on its own. A pretty reasonable histogram for understanding the distribution of a numeric variable. Next, I'm going to show you a box plot. There's a function just called box plot that can take as its argument a single numeric vector as well. And I get a box plot of the salary variable. There are other more interesting ways to use the box plot function, but I'm just starting with this one for now. I can generate a scatter plot using the regular plot function. This function can do quite a bit. It doesn't always generate scatter plots, but here I'm showing you one way to generate a scatter plot using it, where I've supplied two arguments, both numeric vectors of the same length. The result is that we have height on the x-axis and salary on the y-axis. We can get the same scatter plot in a different way, this time using a formula as the first argument. At first, this might seem more cumbersome, but I think most of the time this is actually a more convenient way to use the plot function to get a scatter plot. So the first argument in this case is salary tilde height, a formula just like we used in the LM function. And we've supplied an additional data argument to tell R where to get those two variables, the negotiation study data frame. In the previous function call, I specified negotiation study $sign prior to both of the variable names, which is a reasonable way to retrieve each one of them as its own vector. But here, the formula argument allows me to call this plot function with a pattern very similar to the call to the LM function from just the end of the previous video. With that plot still visible, I can add a least squares regression line by calling the AB line function with an LM object. There are also many ways to use AB line, but in this case I'm showing you a version where I supply one argument to this function, and that argument is the object created by an LM function call earlier. So here I called LM with salary tilde height as the formula argument and stored the result with this name, salary height model. And then down here I plotted that same formula as a scatter plot. By calling AB line with that regression model as its argument, I add a regression line to the existing scatter plot that corresponds to the relationship between height and salary. This is the least squares regression line from the regression model that uses height as the sole predictor of salary. R does not necessarily care that the scatter plot that we added it to actually had the same height and salary variables plotted. So you should make sure to only call AB line with an LM object when your scatter plot already logically corresponds to the result of that LM model. We will talk a lot more about this kind of plot and this kind of model next class. Next, I want to talk a little bit about categorical variables. Height, we've seen, is a numeric vector, and we can double check that by calling the class function with the height vector as its argument. This tells us that it's an integer, or it's a vector of integers. Race is a character vector. The race column in the negotiation study data frame contains character strings, and so the class of that vector is character currently. By calling the table function on that character vector, I can see that the values of race represent a few specific categories. 12 of the participants evaluated an Asian job applicant, 10 evaluated a black job applicant, and 10 evaluated a white job applicant. To more easily use this vector in statistical analysis, I would like to change it to something called a factor, and I'm going to do that here using the as.factor function. Here I've supplied just one argument to that function, the character vector that already existed, which I happen to know will convert it into a reasonable factor. And then I use the assignment operator to overwrite the existing race variable in the negotiation study data frame. Now the class of negotiation study $race is factor instead of character like it was before. For now, it's enough for you to know that a factor is a special type of vector in R, where the values are treated as labels of a categorical variable in statistical analysis. I will cover this idea in much more detail next class. To include race in a regression model, I can simply list it on the right-hand side of the tilde in the formula specification, just as I would a numeric variable. Here is a summary of this salary race model that had this salary tilde race formula. And we can see that R automatically generated two indicator variables representing the race variable because it is a 3-category factor. And we're going to talk a lot more about how to interpret those kinds of models in the coming weeks. Regression models frequently include multiple predictors. And so, of course, our formula specifications also can include multiple predictors. The plus sign separates predictors in the same formula. And the formula argument to a regression model can have multiple predictors on the right-hand side. So salary is still the response variable here. The tilde still separates the response from the predictors, but now there are multiple predictors separated by a plus sign. An asterisk allows me to include all terms required for a statistical interaction. So here, the function call is almost exactly the same, except I used an asterisk instead of the plus sign to separate these two predictors. And the result that I get is a regression model that included a predictor for height, two indicator variables for race, and two interaction terms representing the product of each of those indicator variables with the height variable. We will cover models with multiple predictors and models with interactions in much more detail later in this class. So if you don't know how to interpret them yet, don't worry. Next, I'm going to talk about logical values and relational operators. Here, I've executed a very simple line of code, 3 less than 4, and the result that I get is just true, because it is true that 3 is less than 4. This is a new type of data that we haven't seen yet in this session. It's a logical value, not a number or a character string, but just true or false. If I ask if 3 is greater than 3, I get false. If I ask if 3 is greater than or equal to 3, I get true. We use the double equal sign to test for equality. So this means, is 3 equal to 4? And the answer, of course, is false. And when we test for equality between 4 and 4, we get the result true. Operators like less than and greater than or equal to are called relational operators. When we use these relational operators on vectors in R, they work element-wise. So if I ask if negotiation study $height is greater than or equal to 170, I'm effectively comparing a vector to a scalar, and the result is a vector of logical values, indicating whether each individual height observation is greater than or equal to 70 or not. All of the elements with true in this logical vector correspond to the same indices that have heights greater than or equal to 170 in the original data. You can use and or with logical values like this. The ampersand character represents and the vertical bar or pipe character represents or. In very simple cases, we can see that these work the way that they should. True and false gives false because they're not both true. True and true gives true. True or false gives true because at least one of them is true. And false or false gives false. The ampersand and pipe operators also work element-wise when applied to vectors. Here I've run a line of code that tests whether negotiation study $height is greater than or equal to 170 and negotiation study $height is less than 180. And the result is a vector of trues and falses where the trues indicate cases where the height of the job applicant was between 170 and 180. The exclamation mark means not, so not true gives false, and not false gives true. Here's that same vector again, with negotiation study $height greater than or equal to 170, and negotiation study $height less than 180. If I apply the not operator to the entire expression that gave that vector, then I simply reverse the trues and falses in the vector. So not, parenthesis, negotiation study height greater than or equal to 170 and negotiation study $height less than 180 gives me a vector of trues and falses where the trues indicate cases where the height did not fall in the range from 170 to 180. These are the cases where the height of the job applicant was outside of that range. And of course, I can get that same vector of trues and falses by asking which cases have height less than 170 or height greater than or equal to 180. Capital T and capital F are abbreviations for true and false. So you can use capital T in place of true and capital F in place of false. You can use logical vectors to work with part of a vector. Earlier, I showed you how you could use indices to work with part of a vector. For example, if I have a vector x that is length 6 and has the numeric values 1, 1, 2, 3, 5, 8, and I want to retrieve just the last half of that vector, I could do so using square brackets in the indices 4, 5, 6, using the colon operator to generate the numbers 4, 5, 6 as a vector. And this retrieves the elements with the values 3, 5, and 8 from the vector x. But I could also retrieve part of that vector by supplying a logical vector of trues and falses of the same length as the original vector in the square brackets. To illustrate, I'm going to create a temporary vector called working subset by combining 3 falses and 3 trues in that order. And when I ask for x and use square brackets to indicate a subset by supplying that vector of trues and falses in the square brackets, I get the last 3 elements of x, just the same as I did when I asked for elements 4, 5, and 6 explicitly here. And that's because the 4th, 5th, and 6th elements are the ones that had the value true in the logical vector that was supplied. This technique for retrieving part of a vector is useful to work with cases that meet specified criteria. When I ask for negotiation study $salary, with square brackets indicating that I want a subset of those salaries, and within the square brackets I have an expression that gives a vector of trues and falses, such that all of the trues correspond to confidence values greater than 9, what I get is all the salaries for cases where the confidence was rated greater than 9. You can also use the which function to get the corresponding indices for those cases. So when I call which with negotiation study $confidence greater than 9, I'm plugging a vector of trues and falses into the which function, and which tells me which indices in that vector have true. So this is the same as the row numbers with confidence ratings over 9 in the original data. And those are also the row numbers that correspond to the salaries shown in this output.